everyone, today we are going to study semiconductors. In our earlier video, we have seen energy band levels, valence band, conduction band and forbidden energy band. In this video, we are going to study type of semiconductors. So let us start. Semiconductors are the materials having conductivity in between insulator and conductors. Silicon and germanium are the two widely used semiconductors. There are two types of semiconductors, intrinsic semiconductor and extrinsic semiconductor. A semiconductor in its extremely pure form is called intrinsic semiconductor. A semiconductor in impure form, which is doped by an impurity, is called extrinsic semiconductor. Okay. This extrinsic semiconductor is of two types. P-type semiconductor and N-type semiconductor. When small amount of trivalent impurity is added to the pure semiconductor is called P-type semiconductor. And when small amount of pentavalent impurity is added to the pure semiconductor, then it is called N-type semiconductor. Silicon and germanium are the widely used semiconductors. Now the thing comes in the mind, how this N-type and P-type semiconductor can be produced. So, in an intrinsic semiconductor, when some impurity is added, is called doping of that semiconductor. So, the added atom to the semiconductor is called impurity, and this impurity may be acceptor or donor. Now, what is acceptor impurities? The trivalent impurities like boron, aluminium, gallium, indium, etc. These materials accept electron from pure semiconductor and hence they are called acceptor impurities. Now what is donor impurities? The pentavalent impurities like arsenic, antimony, phosphorus, these are the materials who donates electrons to the pure semiconductor and hence they are called as donor impurities. So let us study what is P-type semiconductor in depth. Okay. So here suppose we consider silicon or germanium. Here we have taken a silicon. Okay. So the atoms of silicon have 4 electrons in their outermost shell. Okay. In silicon crystal, these electrons are shared by the neighboring atoms and hence strong covalent bonds are formed. Okay, this is bonded with this will be bonded to some other silicon, this is again bonded to another silicon. So the bonds are so strong that no free electrons are available. And when we add some impurity, we doped a material in this and say we doped aluminium or what we can say, aluminum is added to the silicon as an impurity. The atoms of aluminum have 3 electrons in the outermost orbit. Okay, 3 electrons means what? One may get share with this, one may get share with this, and the another may get share with this. Means these 3 around each electron forms covalent bond with the neighboring atom, and one covalent bond around each aluminum atom has an electron missing. So suppose when we have aluminum atom over here, we may have another aluminum over here. So for every atom, this aluminum, one axis electron, one electron is missing. So the absence of an electron is called hole. Thus, this hole appears to move in the mixture and can conduct electric current. Its conductivity is not as high as that of metallic conductor, and hence it is called a semiconductor. The conductivity is due to the motion of the holes. Hence, the semiconductor is called P-type of semiconductor. Now, let us see what is hole. What is the concept of holes? In the earlier slide where we have seen an empty space, that space is nothing but a hole. Or we can say deficiency of negative charge can be treated as positive charge. Holes act as charge carriers in the sense that electrons from nearby sites can move into the hole. Holes are usually heavier than electrons since they depict collective behavior of many electrons. Now let us see N-type semiconductor. So suppose in this we have again a silicon. The atoms in silicon have again 4 electrons in their outermost shell. Okay, as we have seen in the earlier case, silicon have 4 electrons in their outermost shell. In silicon crystal, these electrons are again shared by neighboring atoms, and hence strong covalent bonds are formed. Okay, these bonds are strong bonds. Okay, silicon-silicon bonding. The bonds are so strong that no free electrons are available. But when we dope this silicon by the impurity as arsenic, we doped this silicon by an impurity arsenic, then what will happen? Arsenic have 5 electrons in their outermost orbit. 5 electrons in the outermost orbit. That's why what will happen? 4 of them will be shared by the silicon. Okay. Out of these 5, 4 electrons will be shared by the neighboring atom and covalent bond is formed. Then what will happen to the 5th one? The 5th electron remain free to move about, and so the mixture or this material, which is a doped material, conduct electric current. Its conductivity is not as high as the metal, and hence it is called semiconductor. The conductivity of this material, which is doped by arsenic, is due to the motion of holes having positive charge. That's why this is called as conductor, which is N-type. Okay. Now let us see the Fermi energy level diagram for intrinsic semiconductor. What we have seen, intrinsic semiconductor is a pure form. Okay. Intrinsic semiconductor, it is a pure semiconductor. Okay. And pure semiconductor, we have seen the conductivity levels. Okay. The pure state of semiconductor, that is silicon or germanium, they have extremely low conductivity. At 0 degree temperature, it behaves as an insulator. But when the temperature is at room temperature, some of the covalent bond breaks and electrons become mobile, and that's why this forbidden energy gap is in between the conduction band and the valence band. Okay. So here we can observe that here it is a valence band, this is a conduction band, and the Fermi energy band, Fermi energy gap is lying in between the two, or we can say it is in the center of the two. Okay. So what we can say, first of all, we'll define what is Fermi energy level. We have seen earlier in earlier video, it is the term which is used to describe the top of the collection of electron energy level at absolute 0 temperature. Okay. So as we have seen, intrinsic semiconductor behaves as an insulator at 0 degree temperature. Therefore, there are no free electrons, but at room temperature, conductivity increases due to the electron pairs produced. Now, let us see the Fermi energy level in N-type semiconductor. So, as we know, basically semiconductors are the insulators, isn't it? But N-type semiconductor means we had done the doping. So at room temperature, almost all the electron of pentavalent impurity jump to the conduction band. Thus, large number of free electrons are available in the conduction band in N-type semiconductors. Due to large number of free electrons in the conduction band, the probability of occupying the energy level towards the conduction band will be more. Hence, the Fermi energy level is shifted towards the conduction band. Here we can observe very well, this is the valence band, this is conduction band, and the Fermi energy level is towards the conduction band. Why? Because we have doped the pentavalent impurity and more number of electrons are towards the conduction band. Okay. Now, let us see the Fermi energy level for P-type semiconductor. At room temperature, large number of positively charged holes are created inside a P-type semiconductor. Therefore, the probability of occupying the valence band, this is the valence band, okay, this is the valence band, is the probability of occupying the valence band is more, and thus the Fermi energy level shifts towards the valence band. This is all about semiconductors. With this, I stop here. Thank you.